So we have grid with rods, and this rod has type 1, 2, 3, 4, 5, 6 types. Each type has its own unique shape, and we want to answer the question: can we travel with rods from the top left to the bottom right corner? So my intuition was union find, and we just go row by row, cell by cell, and we connecting these rods together. So if rods has some type and some shape, we just connect them to according to this type. And finally, we checking if our root in the union find or 0 item equal to the last item. So this is a solution. Let's look at the code. So this was my code. It's pretty simple idea, but the implementation can be tricky. I over-engineer this. It can be simpler. And I also spent almost 30 minutes just to debug my code because I didn't pay attention. So now, what kind of mistakes you can make? So what I make? The first mistake is if you have a rod with some type and you're trying to connect it, you have to check if the cell you're trying to connect it actually supports your cell. So only if you, for example, you're connecting to the top, you have to check if the cell you're connecting to is has the way to the bottom. And the same idea for all other cells, all other directions. So this can be like this. This is the first mistake that I forgot to check. Actually, I didn't have it in my mind, so I was kind of blind on this corner case. Let's look at the code again. So I use this extra helpers. It kind of screams about something is wrong with my intuition because it's too much code. Now, another idea is that when you iterating with a union find and connecting components, you don't have to connect left and top because you are already iterating from left to the right. So your left cell is already connected and you're iterating row by row. That means your top cell is already connected to its bottom. So minus 2 extra checks. It's kind of optimization that would allow you to shorten your code and shorten your runtime, but it didn't improve all notation. So actually, let's talk about all notation. It is O of nm for the time complexity and same for the space complexity because we're using union find. So this solution was accepted, but it was super slow because it used Kotlin lambdas and they are kind of extra object in runtime. Now let's look at some interesting implementations. So the interesting idea is that you actually don't have to check all the cells. Imagine you have the grid and your first item is just connect left and top. So immediately you can drop or you can exit early. And if you think about it a little bit more, then you will see that you actually can only go one single way. Any way that any cell has only a single exit and single enter. That means you don't have to use no DFS, BFS, several ideas, no QS. What you need is you need your current direction, so your direction plus the type of cell that you have. Like if you have this, your direction is green, and the type of cell, for example, this one, and it will tell you where can you go. Now let's look at the solution or implementation, I would say. So this is a super golfit implementation. Now let's start with not golfit version. So the first was already golfit, but not very much. So we're using this T as transform or transition matrix. So we have 6 types of figures, 6 types times 4 directions. And we could say that each type of this 6, like 1, 2, 3, 4, 5, 6, has 4 directions that it allows, like this, 4 dots inside each section of 6 types, and each type has only some allowed directions, only 2 of them, of the 4, and each type has compound or matching types. Or matching directions. So this is like not types, directions. So let's look at this. As you see, the numbers are from 0 to 3, it is directions. And we tell, for example, the type 1, 1, 2, 3, 4. That 0 is first empty type, and the first type is 1, 0, 1, 2, 3, so this 0 and this is 2. So the type 1 type has, if your current direction is 0, you didn't change it. If your current direction is 2, you didn't change it. So basically type 1 is just, I would say, horizontal or vertical line. So that is kind of how it works, and then we have to actually check 2 ways, because of the first cell can be entered from the left or can be entered from the top. Now this is a first check. It is about if your current type is some mask, bit mask. This is a golfit version, and you check I to 0, it is about, if you're going from the left, your bit mask is 82. If you're going from the top, it is 28. You're checking if you're bit in this bit mask. Now, the actual loop of your path is that you take a new direction, you incrementing your x and y, then you check if you're out of bounds or if you arrive at 0. And if you arrived at 0, that means you are in a loop, because if you have a loop, it will be back to the 0. Why? Because each type has only one enter and one end. You can't have some loop that goes not to the start. It have to be to the start. Now, I would ever say that type 4 is the only type that is a start that can be in a loop. Now, what we do next is we are looking at the changed direction with our transition matrix, and this is how we are taking it. So it is four directions. That's why we multiply by 4. Basically, as I described earlier, and then we checking if it is allowed move or not. If it's not, it's not allowed. Then we check if we arrived at the end and return true, and then we can mark them, grid with zeros, or we can skip it. In my final solution, I skipped it entirely. Let's look at this. Maybe at Rust. Rust is simpler. So we have 2 ways to the left, or from the left and from the top at the starting position. This is a bit mask. 466 is so you are taking this first type plus current direction times 4. This gives you a bit, and then you check in this bit. So 466 is allowed bits in allowed masks. Now you go to iterating from the start position. I use successors in Rust just to be shorter, and then the idea is the same. You use X, you use Y, you taking the next step, then you taking the next direction, and this question mark is what gives successors result of none. Then you checking if your direction is allowed. So if it would be dot, it would be less than 0. Now then you check if you arrived at the first cell, x and y 0, and if it's okay, then you go on to the next, and then you check of the successors first, that is the last cell. So this is the solution. Now let's look at the Kotlin, and this is my first union find solution, but kind of golfed. I removed the connection to the left and to the top, and I simplified, or maybe not very simplified, but definitely shortened the code of the bit mask checks and types. So this is like super hacky version, I would say, because 84 is bits of allowed cells that can go to the right, and this is gx plus 1 percent 2. What it is? It's about types of 1, 3, and 5. So not, it's just to not write very long line. This is the same for the in 2 up to 4. 2 of 3, 4 type as the current cell that can go to the bottom, and the mitten cell is 100, then shift right, and then end 1. 100 is bits of 2 to the power of, and then ABC, some types. I already forgot what are they. And then you connecting them. This is a simple unified. This is using path compression. So this is it. I also can show you a kind of coarse implementation of what I did with Rust, but in Kotlin, and it's kind of very ugly. I used run catching and is success. Then I use this division by 0 just to exit early. So this is not what I publish, but it's kind of short too. So that's it for today.